Okay. So, let's talk about Swift concurrency. So dispatch queues were kind of legacy. They existed before Swift did. They were something that was built using what's called Objective-C, which is the old language you used to build iOS and Mac OS things on. It is still in use. There is interoperability between it and Swift. You might run into it if you do native iOS development. There will be like one single lecture about Objective-C, and you will get to see why people prefer Swift. But that will be much later in the course. For now, know that dispatch queues and the way that Swift handled concurrency in the early days had a lot to do with how it was done in Objective-C. Swift is very heavily focused on being a language that is considered to be safe if you compile it. If you are able to compile it without errors, it wants to be safe. It wants to make sure that you feel like it's not going to crash randomly, right? In practice, it does crash randomly, right? Or what feels like randomly all the time. But it avoids a lot of the kinds of errors that can lead to crashes that you would run into in other languages. Things like null pointer exceptions tend not to happen in Swift unless you use the exclamation mark to force unwrap something that's nil, in which case that's exactly what happens, but you took that risk when you used the exclamation mark. Swift as a language has decided to... Did this die? No. What are we doing? There we go. That was weird. Okay. It has language level support for building concurrent code on threads. So rather than having a library, which is what dispatch queue was, that was something that you import. It was something that you basically use classes and structs and other types that were created for you, right? What Apple has done in the last 4 to 5 years is basically built, and I'll get the mouse off of there right now, basically built a way to handle threads and concurrent code at the language level rather than one level above it, which is with a library. So you will be using keywords like class and struct. You will be using language features like trailing closures. Things like that will now exist for you that make it easier to write safely concurrent code. Code that, if it compiles, will not have concurrency issues or concurrency crashes, at least. You might still have logical problems, but that's something for you to figure out. You're the programmer. So Swift concurrency is focused on statically checking for safe concurrency. Basically, if it compiles, it's safe. That's a point I already said. I love to repeat myself with my bullets. To do this, it has this concept called concurrency domains. Basically, specific scopes that the static compiler looks at and says, okay, if there are if there's mutable state within here, and mutable state is just a way of saying memory that can be written to, right? If there is memory that can be written to in here, then this is safe as long as the things modifying it are within the same concurrency domain, meaning running on the same thread, or not exactly the same thread, but a thread that's like close enough to safe or something like that, right? It's kind of handling all that for you under the hood, but the main thing to know is if you're within a concurrency domain, it is safe to modify memory within that domain without having to worry about some other concurrency domain trying to access and read it and causing a crash while you're writing to it, okay? That's really key. They call them concurrency domains. In my head, I always call them concurrency silos. Like the silos outside of a barn, right? With like the grain in them. You know what I'm talking about? Those like paintings. They got the like those kind of tall like thin things and the round tops. I don't know. Silo imagery just works better for me than domain, which feels like a really generic word. However you want to think of it, it's basically just this kind of border that gets placed around code that says, okay, everything in here is within the same domain. And within this domain, concurrency is allowed and safe. But outside, we have to do some stuff to cross those boundaries, okay? And there we go. The other thing is that when you want to cross those boundaries, to send data between the two domains, you need to use a special protocol for that, which is why we learned more about the where clause and conditional where earlier. I don't have slides showing the cool things you can do with it and that protocol, but suffice to say, it's relevant in that way. Cool. Any question about kind of like this high-level stuff before we dive into some code? Cool. Wow, my clicker is really slow today. I don't know if it's like not responding or what. All right, async await. So the first thing you'll learn about Swift concurrency is the async await pattern and the async and await keywords. It's both a pattern and a keyword. This is intended to kind of solve the problem that we had before. You recall callback hell. This was what we were just looking at, right? These functions that have all of these to-do queue.asyncs that we have to then nest the calls to moving forward. With the async await pattern, we don't need to do that. Remember how when we first were looking at this function, we thought, man, it would be great if we could just return the value once we get it, right? Wouldn't it be great if we could just have the return type be our type, and then we just return it, and it's all good, and it just returns it when we have it? Well, with async await, you can do just that. So let's modify fetch to-dos. This is what that same function looks like in Swift concurrency. It's much smaller, it's much simpler to read, and it's much easier to reason about. If you look at below, at the bottom here, this is how you call it. So you'll note two things here that you've not seen before. First, this async keyword. The async keyword comes after the parameter list and before the return indicator. Okay, that's where it goes. That's the same place that the throws keyword goes if you remember throws. Async and throws have to be written in a specific order if you are writing a function that is both async and throws. The compiler will tell you, though, if you get it wrong, it'll tell you how to fix it, and it even gives you a handy button to fix it for you. So don't worry too much about it, but just know that that's a thing. So basically, we have now written the same kind of code, right, where whatever thread is calling this, await fetch to-dos, will now sit here and pause execution. It will await this function to complete, which kind of sounds like how synchronous code works, right? It's basically the same thing. The main difference is that we're pretending that this is a network call that's actually going to take a long time and we are kind of doing in a background sort of way, right? But here, out here, this context, this scope, this execution thread is going to wait for this to call. In this case, that's main, just because we're doing this in a main.swift file. Typically, you will not be calling things with await from main.swift. You'll be doing something there that kind of switches you from synchronous to asynchronous code, right? But that distinction is, we'll look at that in a moment. So that's how you do it for fetch to-dos. Okay, well, how do we do it for average completed stars? I mean, this one takes in a parameter, right? It's a little different, you know. Is it more complicated? Is it harder? Is it more difficult? Is it harder to read or reason about? Oh, look at those characters. I didn't catch them. No, it's not. And same thing for upload. It's exactly what you wanted it to be when you were first thinking about dispatch or asynchronous code. You just wanted to write the function. You just wanted to make your computations. And you just wanted to return the type that is the result from the computations. Are these long running? Do they take time on the background? Who knows? Not really relevant. That's not something you, as a function, should care about. It's not your job. Your job is just to do the thing. And then you have this async keyword to indicate that you, as a function, can be thrown into the background thread somewhere. You can be run asynchronously if you want, right? Or you're doing something asynchronous, or you're doing something that takes a really long time, so you should be called asynchronously, right? So we have this. Now, again, this looks a lot like code that just doesn't have these async await keywords, right? If you just removed these, this would do the exact same thing in the exact same way. And that's because we're not actually doing anything asynchronous in these functions, because I haven't taught you how yet, right? But let's pretend that we're calling a network, right? Or pretend that we're saving to disk or whatever, right? Then this is what would look like when you call it. So this is how you solve callback hell, right? This is the solution for callback hell, which was the problem with dispatch, okay? You get this much easier to read and reason about lines of code that just kind of work in a way that looks synchronous but is not actually once we start to look under the hood. So let's talk about context. You'll recall I kind of railed against the word context in like the first class when I talked about scope. I'd prefer to say scope, but Swift documentation uses the term context, so I guess we will too. Context means the surrounding pieces of code, so the scope, or not just its current scope, but all the things it inherits from outer scopes, right? Basically everything about the current place you are in code is the context. If you're in a function that's inside of a class, that's an instance being used on another class, that's all context for that piece of code, right? So our context for this piece of code right now is that we are within a function called firstReminder, and this function is running asynchronous code, okay? This keyword changes all code within this block to be in an asynchronous context. Swift now runs code in two different ways. The compiler checks things differently if you are inside of a context that is synchronous. That's going to be really hard. Like I want to say synchronous context versus asynchronous context. Awful. But if you're within a context that is synchronous, the code compiles and runs in a different way than if you are in a context that is asynchronous. Okay? So here, this function is asynchronous, and the code running within it is in an asynchronous context. This code, excuse me, stop it, pass, Dan, stop it, went too far. All right, this code is in a context that is synchronous, okay? Print reminders does not declare async, which means the code runs the way that it's been running for us this whole time, the way that you are used to using it, right? That is the synchronous context. I'm just going to use the instead of a. That is the synchronous context, okay? As a result, if you call a function or a piece of code that is considered to be within an asynchronous context, you'll get a compiler error. You can't call asynchronous code from synchronous code directly. You have to do something to help translate. Or you can just make your synchronous code asynchronous, which is mostly how Swift tries to handle this with the new concurrency stuff. It kind of wants you to write most of your code within the asynchronous context. But, you don't have to. And in fact, you won't be able to most of the time because you'll be using libraries that are synchronous. So you're going to have to be able to bridge between the two contexts, and that's going to be a lot of what we look at later on. For now, though, recognize that if you're calling a function that declares itself as asynchronous, and then you are also within another asynchronous context, then when you call it, you need to use the await keyword. What this is doing under the hood is basically saying, hey, I want to call firstReminder, but I don't need to do it immediately. I can do it whenever the thread is free. Whenever the current executing thread that we are working within is free, I can call that. And Swift's language level features can when it compiles, it'll basically be like, oh, okay, we'll try and run you as fast as we can. If we need to make a new thread for the thread pool, we'll do that, and you can run concurrently or whatever, right? But on the current executing thread, you need to wait. I'm sorry, I think I just reversed that. Apologies. What the await keyword does is it pauses execution on this thread until you get your response from this. And by pauses execution, I just mean it puts that execution inside of this one, right? So like Out here, you're executing, and then here you go in and now you're executing in here on that thread. The thing that I said before, it's true and relevant when you're when you're dealing with two different async contexts, but in this case, because you're calling this function from within an async context, then this function gets the same async context as this function has. That might not make a lot of sense right now, but it will shortly. Okay, you went too far, again, as always. I'd like to go back. Thank you. It's like it's delayed, like it's getting all of my inputs like 5 seconds after I do them. Okay, so let's take a look at this getReminder function. We saw this earlier, right? It has this escaping closure. It does this async after deadline time, and it calls the closure and prints, it calls the closure and passes this changed string in, and then here in the closure, once that gets called, we print that out, right? Cool. Very cool. Very, very dope, right? This is how you do it with dispatch queue. Let's look at how you do it with async await. It's much simpler, a little easier to read, kind of more straightforward, right? Oh, that was weird. So here, we're going to do this await get reminder of second reminder in 3.0, right? And then we are also calling within here, this async context, we call sleep uint32 time. This is basically we're sleeping the amount of time that gets passed in, and sleep takes in an int, so we have to cast the double. Don't worry too much about it. So this is going to pause the thread and pause the execution for 3 seconds or whatever until we come out, and then we come here, right? So this is going to print, as you might expect, first reminder, then second reminder gets brought back, second reminder, and then last reminder, right? Do I wait? Do I not? Do I click? Do I not? Right? Yeah, I hope it's not. I mean, I charged it before I came. Okay, here it's supposed to last for like 10 hours. And the laser seems fine. So, all right, so first reminder, then after 3 seconds of waiting, second reminder and last reminder. Cool. As we would expect. Now, let's look at something called task.sleep4. Before we do that, though, we're going to just take this function that we were creating, and we're going to build a little struct around it. So now, instead of calling this getReminder function, we're going to instantiate a struct, which is a value type. So we're just going to create these values all together in memory. And we're going to group them together. So we're going to now have, instead of passing in a time necessarily, like if you do pass in a time, great. And if you don't, we'll pick a random one between 1 and 3. You get your message. And then, that type instance gets stored into this reminder constant. Now, when we call reminder.load, because this function is async, then we return the message just directly, and then we can print that out, right? Again, you remove async await, this just compiles, right? Exactly the same. Here, we can do, this is how you sleep in the async await context. Before we did that kind of sleep and you had to pass in an integer. Here you can do this cool thing where you say task.sleep4 and then you do this, you call in enum.seconds or .milliseconds or .minutes and then you pass a number to that, right? It's a little bit nicer way of doing it. It can throw, so you need to do a try, and it is async, so you need to call await, right? And it can only be called from an async context. But that's kind of how you sleep now. So this kind of does the same thing as the previous function. But now we have a struct, so we can create instances that can load and, return their message in an asynchronous quote-unquote manner by simulating things taking longer than they actually do by sleeping. Cool. Okay, so now that we have this kind of structure, let's take a look at doing things serially. So here we have let reminder1 equals reminder, and let reminder2 equals reminder, right? So we get our 2 reminder instances, and then we call print await reminder1.load, print await reminder2.load, right? What this does is it prints first reminder, then it goes to print this, but it has this await reminder1.load, right? And so this, we enter reminder1's .load function, and we see that, oh, reminder1 has a time of 3. We need to wait for 3 seconds, right? So We come here, we wait for 3 seconds, and then we print second reminder. Then we come here and we wait for 2 seconds and we print third reminder, and then we print last reminder. This will look very similar to some of our earlier examples. You can probably guess what's coming next, other than just the example of what gets printed when. This is how you can do things in parallel. So if you want to have these run concurrently, if you want to have your code executing at the same time, basically in the way that you would with dispatch queues, the way you do that with Swift concurrency is with async let. So when you use the async let keyword, you are creating what's called a task group, and we'll talk about tasks and task groups shortly. And you're saying, hey, we're going to start declaring a bunch of things that need to all happen together at once. And then as soon as we try and use anything that we declared within this kind of group context, then at that point we block and we wait to get everything back. Okay? So what this is saying is async let reminder 1. All right, we've created a task group, and now we're going to put this await reminder task into the task group. Awesome. As soon as it's in, it starts executing. Then we're going to take this, we're going to have async let here, and this is saying, oh, okay, we haven't used reminder 1 yet, so this is also getting added to the task group. So as soon as this task gets added, it will also run immediately. And then we take this await reminder task dot load and we add it, right? And so these two tasks both get added to a task group, one right after the other within milliseconds, right? And then they execute at the same time. We can do a bunch of other code after that while those are executing, right? These two calls don't block. We first block the thread and wait to continue the first time we try to use either of these constants or variables. And because these constants or variables represent tasks within a task group, we have to use the await keyword and say, oh, hold on, this is asynchronous. This is an asynchronous task group. I need to wait for this, right? And that's what the await keyword does. So you can basically have these things, print first reminder, then this reminder call. These will run simultaneously. You can do a bunch of stuff after that, and then you can print await reminder 1, await reminder 2. And the first time you use either of these things that was created, you are basically saying, cool, we're done writing to that task group. We're not going to put anything else in it. Now we're trying to use that task group and block the thread until everything in that task group completes running, right? But those things do run concurrently. So the thing that this prints, oh, and I have comments that say exactly what I was just saying. Can we move forward, please? Next slide. There we go. Okay. So what we see here is that the first reminder prints. Then after 3 seconds, which you'll note is the longest amount of time that was passed to the task group, right? Each of these tasks is running concurrently, but we're not going to do anything until all of them return, which means whichever one is your longest task is how long it takes before you unblock, right? So we're going to wait for 3 seconds, and then we're going to print second reminder and third reminder almost immediately. And this is how you run things concurrently using async await. Or not async await, using Swift concurrency. You use async let in order to do things serially in Swift concurrency. Again, this looks like synchronous code. It reads like synchronous code. You wouldn't know it wasn't synchronous code if it wasn't for all of these async and await keywords. Those are what clue you in that this is running and capable of running asynchronously. Wow. Pulled that from the comment. Okay, so tasks. I talked about tasks. I talked about task groups. What are they? Basically, tasks are these kind of pieces of code that are scheduled to run concurrently. These are a lot like the closures that you pass to dispatch queues. They are not exactly the same. Tasks in Swift have this concept of being structured. So you can have tasks that nest inside of each other. Every time you call await, you use the await keyword, you are creating a new task, okay? That creates a task implicitly that is going to run. When you use async let, you're creating a task group. And a task group doesn't complete until every task within it is done. As a result, you can also have within a task group another task group, and inside that, another one, and so on and so forth. And you can chain all of these tasks together so that you have this, what's called structured concurrency, where things work in a kind of nested way that makes intuitive sense. But sometimes you're working with synchronous code, and you just can't immediately use async. If you are modifying a library or you're working within, like if you're implementing a method for a protocol that is not asynchronous, you can't just add async to the function definition. If you do that, then you will no longer conform to the protocol that you adopted because you've now written a different function. You can write a new function that's async and then maybe call that. And the way you do that is by using what's called an unstructured task to schedule something into the asynchronous context from the synchronous context. So the way that looks is very similar to dispatch queues. It's this. You use the task type, you pass it a trailing closure, and now we are within we are now within the asynchronous context, or an asynchronous context, okay? Here, this function is in the synchronous context. It is not asynchronous. It doesn't have the async keyword, okay? So here after we define everything, we call print reminders, right? And then we enter print reminders, and this is all happening synchronously. We do this, then we do this, then we print first reminder, and then we kick off this task. And this task takes this block of code and then schedules it to the asynchronous kind of language stuff that's happening and sends it out to go do some work, which is very similar to how dispatch queues work, but it's very abstracted. You're not creating queues, you're not accessing the main queue, you're not doing anything else. You're just scheduling a task. And the thing about tasks is they tend to inherit priority and the thread from where they get called, right? So this is like an asynchronous task, but it's kind of running on main, but kind of not. You actually can't call thread.current from code that's asynchronous. It won't let you. They don't want you messing around with threads. They don't want you looking at threads. That's too fiddly. They want you to just be thinking about writing your spinner and making it spin majestically while you download things to display to your user, right? They don't want you thinking about scheduling in queues and threads and exe bad Alex. That's not fun. UI is fun, which we'll see, but that's in 2 classes. So for now, recognize that if you want to go from synchronous code or the synchronous context to asynchronous code or the asynchronous context or an asynchronous context, you use an unscheduled task to do that, typically. Or sorry, an unstructured task to do that. Oh, nope, back. Here we go. So again, we get basically the same thing here, right? But the main difference is because we've sent this task out to go run asynchronously, right? Again, then we print last reminder before we execute anything within here, right? Just as we did with dispatch queues. So once again, you do end up with that situation where if you send things out into unstructured tasks, you can't really get anything out of them. You can't get returns out of them without doing something crazy like passing in closures, which Swift doesn't really want you to do and tries to stop you from doing unless you set that closure up in a very safe, specific way, which we'll be looking at in a bit. Oh God, it's 3 o'clock. Okay, I'm going too slow. All right, I'm going to speed up. Structured tasks and 408 in. So structured tasks can also do this kind of thing where you basically have a for loop that kind of executes sort of asynchronously. Here, we are creating a task group explicitly. Before, when we were using async let, we were creating a task group, but it was implicit. Swift was doing it behind the scenes. Here, we are manually doing it by hand. We're saying await with task group of string self, group in. This of string self is saying that each task in the task group should resolve to a result of string. That's the goal of the group. We're getting a bunch of strings, okay? You will often find that you'll be using a protocol or something like this, So, yeah. And then this group in, this is the group itself. So this is the group of tasks. It's like, consider it an array of tasks. If you want to schedule a new task into the group that is to execute, you add it to this group parameter that's being passed into this closure that you're creating in with test group. So then here we have this reminder in reminders. So we've got this reminders array. It's got 3 reminders in it. So we're just going to iterate through that, and we're going to create a new task for each one. And in that task, this code within here is, considered to be asynchronous. Okay. So we have, because reminder.load is async, we have to call await reminder.load, right? So this is basically saying, hey, schedule a new task. This is going to run concurrently to any other tasks that we add, and it's going to just wait for this and return that value, and that's going to be the result for that particular task, okay? We're going to do that for each of these. So we're going to do that for 1, 2, and 3, right? Then you can use this for await text in group. So because the group tasks are all supposed to resolve to a type of string, right? Which is what reminder.load here does return a string, okay? So we're resolving to the type string. Now, when we iterate through group, if we do it using the asynchronous for loop, okay? The asynchronous for loop is for await in, text in group. Then what's happening is we're saying, oh, okay, run this code as soon as any of these tasks are done, run this code for that task. So rather than blocking and waiting for every single one to finish, right, we can have this run after each one pops, okay? And this is where you're starting to get into some of the really interesting stuff where, like, when you're scrolling, you might notice, like, oh, the images are loading out of order, right? They're coming in, and it's based on how big they are and how long it took the network to get them. And you can do that sort of thing using the for await in loop. Basically, this executes as soon as this task completes, but only each individual task. But it's the same code for each task, which is pretty cool. So what would we expect this to print, right? We would expect this to print out something when I click the button. Here we go. So after 2 seconds, we print last reminder. Then the next reminder that's going to print prints 3 seconds after we kick off the tasks, right? So rather than saying, oh, after 3 seconds we print first reminder, as you might expect if we were doing this in the kind of more serial way, this reminder is now going to print after 1 second, because 2 seconds from 3 seconds is 1 second. It's math. 3 seconds after the start, we print first reminder. And then 5 seconds after the start, which is 2 seconds after we print first reminder, we print second reminder. So now you're starting to see kind of, the way that Swift concurrency handles these sort of actually asynchronous cases rather than just pretending to be asynchronous and then actually just doing things in exactly the same way its synchronous code would, right? So this is a way of manually creating structured tasks with and a group of them. So, tasks within a task group, and then doing things as those complete, right? And then at the end, this task group does return a value. And that value is an array of strings. And so it will return it, because we're awaiting. So we're waiting for this task group to finish, which is waiting for all of the tasks within it to finish. And as a part of them finishing, they print this text, right? But then each string that we return from this async load is returned in an array from the await. It's not technically an array. It's some really weird, hard to read and understand type, but you can pretend it's an array. It's close enough. Cool. Any questions about task groups? I've got 10 minutes, so we're pretty close to the end, but so any questions here? Okay. Actors. So remember we talked about concurrency domains. There's a problem. When you have types that are not quote-unquote sendable, which is what Apple calls things that are safe to cross concurrency boundaries, then you cannot send them across concurrency boundaries. So what does that mean? Okay, so here we have this reminder, right, class that we've been using, okay? It has an initializer. The initializer is asynchronous. It waits for a little bit before it initializes things, okay? This call here from main.swift will cause an error. It will say non-sendable type reminder returned by implicitly asynchronous call to non-isolated function cannot cross actor boundary. Okay, what does that mean, right? Basically what we're saying is the initializer returns a reminder type of instance, okay? The reminder instance is a class. It's not a struct. We haven't talked too much about sendables yet, but classes by default are not safe to cross concurrency boundaries because they're reference types, which means if I send you a class, and I'm over here, I'm a concurrency domain, I send that concurrency domain a class, we can both start editing the same memory, and that can cause a crash, right? So by default, the compiler stops you from doing that, right? So you get this error. So how do you fix it? Well, there's two ways. The first way is to use this main actor. Sorry, there's a few ways, sorry. But the first way is using this main actor thing, right? If you declare this as main actor, what that's saying is, oh, okay, this class, it's not in some random concurrency domain. It's not in some indeterminate concurrency domain. It's in the main concurrency domain. Only things that are in the main domain are allowed to edit it, which means if it's that they're all executing on the same thread, okay? So anything that's in main is going to be running on the same thread and editing things on the thread, right? That's fine. It's all on the same thread. It's all safe. Cool, great. And now in main.swift, which by default is in the main concurrency domain, then this is now safely accessible and we can do stuff with it, right? And we don't need to call await or anything because we're in the same concurrency domain. I mean, we need to call await here because that's async, but like other things, right? So the other solution, click. Here we go, is to make it an actor. Actor's a new keyword. Excitement. It's a new type of type. Remember how types are structs and enums and closures and classes and functions, technically, although people mostly just say closures when they're saying that. Actors are a new kind of type. Say hello to actors. Actors are your concurrency friends. You define actors basically exactly as you would a struct or a class. They have properties on them. They have stored properties, computed properties. They have methods. They need initializers. They deinitialize. They do all the same things that classes and structs do. The main difference is that when you create a class, you are defining a new concurrency when you create an actor, you're defining a new concurrency domain. So you're saying, oh, okay, cool. So you've got that main concurrency domain over there. That's nice, that's dope, that's cool, whatever. I have my own domain over here. It's the reminder concurrency domain, okay, right? And so things happening in the reminder domain are okay. So anything scoped within reminder can act with impunity on message, stars, and time, the stored properties, because those are mutable state, right? Those are mutable pieces of memory that you can edit, that you can change, okay? Because they're pieces of memory you can change, they're dangerous to allow to cross concurrency boundaries. But if you are an extension of reminder, if you are a function within reminder, a method, if you are code running in an initializer for reminder, then you can access these things no problem, You can edit them, you can read them, it doesn't care, because everything within that concurrency domain is guaranteed to run in a safe serial manner, right? So here, now in the main.swift currency domain, when we create a reminder, we have to call await, because this is async. And if we ever want to read anything from that concurrency domain, we have to call await, because we're crossing the boundary. So we're crossing the boundary, and now we're trying to read a property on another boundary, and so that means we have to wait for it, because we might not have access to it. It might be locked down. Someone might be writing to it. Someone within that domain might be writing to it. So we have to wait our turn for them to finish writing, so we can then read it and print it out to the user. And that's what this is, okay? So if you have an actor, and you are trying to access its properties to read them from other concurrency domains, the compiler requires that you use the await keyword. It will tell you, don't worry, you can't mess this up. That's kind of the point. Then, if you try to modify any of the mutable state of an actor outside of it, right, you get this error. Actor isolated property stars cannot be mutated from the main actor. You can't change the mutability. You cannot change the mutable state in another concurrency domain from your own. You can send a message to them and say, hey, when you have a moment, please change your thing. Here's a new value for you, right? And there's a few ways to do that, but by default, you can't just modify it directly. Click, 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 click. How many clicks to get to the center of a Tootsie Pop? Come on. The world will never know. Please. Okay. So let's consider. We have our new concurrency domain here. We also have another class called message. This is not a concurrency domain, it's a class, and we are referring to it here inside of the concurrency domain, right? So in this domain, we have this message property, and it is of type message. Cool. Class is a message type. Sorry. Message is a class reference type. Thank you. So in main.swift, we're still in the main concurrency domain. We can create a message, cool, no problem. It doesn't have any domain rules because it's just a regular old class. And then we can await the reminder here and store that in the reminder constant here, right? So we create a new actor, and you can use actors exactly as you do classes and structs. Instances of actors are very similar, they're just concurrently safe, okay? So then you might say, oh, cool, okay, I'm going to do await reminder.message, right? Just like I was doing before when it was a string, but now it's a class. That should be fine, right? No, it's not fine. It's not okay. Strings are safe. Strings are what's called sendable. They can be sent across concurrency domains because they're value types. They copy. No one's sending a reference to a place in memory. We're making a new place in memory for you over there in your concurrency domain. Ah, this is going around. There we go. Okay. Oh, what is this? No, stop it. Go away, simulator.trampoline. Please leave me alone. What are you doing? Don't allow. Okay. I probably need to get back in here. Okay. Oh, no, I didn't. It's just decided to go. All right. So you can just make this implicitly sendable. If instead of a class, you make this a struct because it's a value type, it can be sent. Value types can be safely sent. Classes cannot. That's pretty much just a hard rule. There are ways you can make classes safe to send, and we're going to look at that, I think, next. Yes. So if you want a class to be something that you can send across concurrency domains, you implement what's called the sendable protocol. The sendable protocol is the thing that you use to indicate that something is safe to send across concurrency domains. There are rules for what things need to do in order to conform to the sendable protocol. And a lot of things adopt it implicitly. They synthesize adoption, like all structs. As long as all of their properties, stored properties, are also structs or value types, so structs or enums or whatever, or are sendable, I suppose is a better way of putting it, then they are also sendable. But if they have a reference to a class that's not sendable, then they are no longer sendable, right? It's kind of like one of those like licenses that's sort of viral, right? It has to, like the GNU license or whatever. It's a different discussion. So basically, you can say this class has to, it's adopting sendable. Now, sendable will yell at you if your class is not marked final. We never really talked about this keyword, but basically that keyword says you can't extend this class. You can't, sorry, not extend. You cannot subclass this class. You can't create a subclass of this class. There's reasons for that. We're not going to get into it. Just know that if you're making a class sendable, you would use final. However, for something simple like this, you'd probably just make it a struct. Okay. And that's it. That's concurrency in Swift. There's a lot more to it. You'll see some of it in the reading. The assignment isn't exactly done. Sorry, there was a lot of code for these slides. So the assignment will be sent out before the end of the night. Normally, I like to have it done so that like when you leave here today, you can see what the assignment is. You'll be able to see it tomorrow morning. That's my promise to you. But your assignment is basically going to be, you're going to be creating something like this reminder, right? You're going to be basically creating code that like prints to the terminal after a certain amount of time. And you'll do it using Swift concurrency. So cool. Okay. Any questions now that we are at the end of class with 2 minutes left? We made it. We did it. Whew. Okay. All right, I'm gonna turn off the recording and then in terms of administrative stuff, I think just the assignment thing and the quizzes. I'm going to be.